This is Module 3 on atoms and elements. Shakespeare, what's in a name? That which we call an atom by any other name would bond as sweet. Think about the names of the different kinds of atoms. We call the different kinds of atoms elements. Some of them are named after places. Plutonium, Neptunium, Mercury, Uranium. These are named after planets. Helium. Helium was first discovered in the spectra of sunlight. So helium is named after the term Helios, the Greek name for the sun. Selenium, the Greek name for the moon, is Selene. How about those named after places on Earth? In Berkeley, California, where many of the artificial elements were first formed, we have americium, californium, berkelium. Of course, others: strontium, thulium, scandium, Scandinavia, holmium. 4 elements named after a small town in Sweden, where these elements are mined. Erbium, terbium, yttrium, ytterbium. There is a small town in Sweden called Ytterby, Sweden, Ytterby, with 4 elements named after it. Polonium, named after Madame Curie's home country. She was not always Marie Curie. She was Marie Skłodowska, was her maiden name. Germanium, europium, gallium, francium. Magnesia was a place in sort of in Greece. Magnesium. Elements named after people. Thorium, curium, mendelevium. Element number 41 used to be called columbium. Elements named after the colors of the rainbow. Iridium means rainbow. Chromium means color. Rhodium means rose. Iodine, because it's violet colored. Chlorine, because of its yellow-green color. Elements have a symbol that represents the name of that element. The symbol consists of 1 or 2 letters. Some of the elements that don't have an official name sometimes have 3 letters. The first letter is always capital, and if there is a second letter, it's always lowercase. Capital C is carbon, but capital C lowercase o is cobalt. Capital N is nitrogen. Capital C lowercase a is calcium. Capital F, fluorine. Capital A lowercase l, aluminum. Capital O, oxygen. Capital M lowercase g, magnesium. So how should we organize the elements? If you had a pile of elements, how would you organize them? Would you put them in alphabetical order? By name? Alphabetically? Would you put them in order by how they got their name? The elements that are named after places in one group, the elements named after people in another group? Or might you organize the elements by grouping the ones that have similar properties? Dmitri Mendeleev in 1869 grouped the elements with similar properties into groups and put them in order by their atomic mass. His first periodic table left gaps where he thought undiscovered elements should go. Gallium, scandium, germanium were elements that were discovered to fill in the gaps on his periodic table. So our periodic table is organized. It's organized in columns called groups or families. For example, group 2A is beryllium, magnesium, calcium, strontium, barium, and radium. These are silvery metals that are somewhat reactive, not as reactive as group 1A, but they all form +2 ions when they form compounds that are ionic with nonmetals. Elements can also be ordered by period. So a horizontal row is called a period. So we would say that calcium is in group 2A and in period 4. Called the alkaline earth metals. Then you have your transition elements, which are in the middle block. The chalcogens, group 6A, the halogens, 7A, the noble gases, 8A. Of course, there are some that don't have common names. Really, within 3, 4, 5, and 5A, the elements actually don't have as consistent of properties. The upper elements tend to be nonmetals, and the lower elements tend to be metals. They transition. You can find tons of periodic tables on the internet. Here would be a place you might go to this website. There are interactive periodic tables where you can click on elements and see real samples. There's a local collector from the Wolfram software company. Wolfram is actually an element name for tungsten. There's a man who works at Wolfram who has a collection of elements, and Wolfram on its website actually has pictures of the elements. You can click on the element on the table and see a picture of a real sample. Here are some pictures from Wolfram's table. Here are the pictures of the alkali metals. Notice they all have similar appearance. Of course, francium doesn't quite look the same because that's actually a rock that contains a very small quantity of francium somewhere within the rock. There isn't really enough francium in the world to create a block of francium. The alkali metals are all soft, shiny, silvery colored. They're good conductors of heat and electricity. They have relatively low melting points. They melt at very low temperatures. They react vigorously with water. In fact, they will explode on contact. Some of them explode on contact with water. They all form oxides with oxygen that are white in color. So this family of elements share similar traits. The alkaline earth metals are soft, shiny metals similar to group 1, but not as reactive as group 1. Of course, they include number 88, radium, which was once used to make fluorescent paint on watch dials. The ladies that would paint the watch dials inadvertently would lick the paintbrushes to make them sharp so they could paint the tiny little numbers on the watch dials, and they figured out that radiation caused cancer when those ladies would get mouth and throat cancers, realizing that it wasn't a coincidence that all those ladies that used to paint watch faces were getting cancer. The halogens, the salt makers, that's actually what halogen means. They have a variety of states and colors, starting with gases, fluorine and chlorine, and liquid bromine, and then solid iodine astatine. Their reactivity is strong, and they form compounds with most of the other elements. We actually have a misspelling here. It's not the Nobel gases, it's the noble gases, group 8, NOBLE. Similarly named to the noble metals. The noble metals, copper, silver, and gold. One property that the noble gases shares with the noble metals are that they are relatively unreactive. They are chemically inert. Very hard to get a compound with these elements. Helium, neon, argon, krypton, xenon, and then the radioactive one, radon. The color of the noble gases, often seen in neon signs, the color of the noble gases are actually due to being excited by electricity. The electrons, when they fall back, give off the color. The gases themselves are colorless. Here's a table that's color-coded. The yellow elements on here are considered nonmetals. The blue elements are the metals, and then the green elements are the ones with properties in between the metals and the nonmetals called the metalloids. Here's a description of some of the properties of metals, metalloids, and nonmetals. Metals and most of the metalloids are shiny, tend to be solids. Mercury is actually a liquid. The nonmetals are not very shiny. Some solids, some gases. Bromine's a liquid. The metals are ductile, which means they can be drawn into wire shape. The metalloids are very hard and will tend to shatter if hammered. Or if you try to change the shape of a metalloid, it just breaks on you. Similar to most nonmetals. Metals are malleable. They can be flattened into sheets. Metals are good conductors of heat and electricity, whereas metalloids and nonmetals are poor conductors. Metals are high melting point in general and more dense than nonmetals. Metalloids have melting points and densities between the metals and nonmetals. Nonmetals have typically low melting points and low densities because of their tendency to be gases and liquids. Transitioning from the elements to the actual atoms that make up the elements. There are a lot of individuals over the years who have contributed to our current model of the atom. In our current model of the atom, we basically have two parts: the nucleus, where the protons and neutrons reside, and the electron cloud. Protons and neutrons have a mass of about 1.67 times 10 to the minus 27 kilograms, which in atomic mass units is about 1. The proton has a +1 charge and the neutron has neutral charge. Electrons have a much smaller mass. It takes about 2,000 electrons to equal the mass of a proton or a neutron. And electrons have a charge of -1, just the right amount of charge to cancel the charge of a proton. Atomic mass units are the appropriate unit for measuring the mass of protons, neutrons, electrons. It's a very tiny mass unit. It's actually the mass of 1/12 of a carbon-12 atom. Carbon-12 atom containing 6 protons and 6 neutrons. The neutron was discovered by Sir James Chadwick in 1932. He determined that atoms of the same element must have the same number of protons, but can have different numbers of neutrons. So we call atoms of an element with different numbers of neutrons isotopes. Once atomic number was discovered, the periodic table was reorganized. Instead of being in order of increasing mass, it is now in order of increasing number of protons. So the atomic number is 1 for hydrogen, 2 for helium, because that's how many protons they have. Instead of the mass of each atom, we have a weighted average of the naturally occurring isotopes of an element listed on the periodic table. So that's actually an average mass on the periodic table for each element. So the reorganization of the periodic table by atomic number is based on the number of protons, which means we really don't have any missing elements. We can add elements to the end of the chart, but since we know we have filled up all of the slots in the table for the number of protons in the atom, we know that there are none in the middle of the table that are missing. Comparing an element of lithium with atomic number 3, lithium would have 3 protons and 3 electrons to be the neutral atom. The most common isotope of lithium has 4 neutrons, but they're could be an isotope of lithium with a different number of neutrons than 4. Carbon's most common isotope is carbon 12, which the atomic mass unit is based on. It has 6 protons because carbon is element number 6, 6 electrons to balance the charge, and 6 neutrons. The protons and the neutrons add up to the mass number of the isotope. Atomic mass, also seen on the periodic table, is the average mass of all naturally occurring isotopes. Even though hydrogen 1 is the most common isotope, the other isotopes raise the average of hydrogen's atomic mass to 1.008 AMU. So that's the decimal number on the periodic table. If we look at the isotopes of magnesium, here are 3 isotopes of magnesium: magnesium 24, magnesium 25, and magnesium 26. In magnesium 24, we have 12 protons. To balance out their charge, we would need 12 electrons. The upper left-hand corner tells us we have a mass number of 24. This isotope happens to be 78.7% of the magnesium found naturally, and it would contain 12 neutrons. 12 protons plus 12 neutrons equals mass number 24. Now let's try to fill in for magnesium 25. 12 would be the protons. Of course, 12 would have to also be the electrons. The mass number is 25. This is the one that's 10.1% abundant. And 25 minus 12 would be 13 neutrons. Magnesium 26 would have 12 protons, 12 electrons, a mass number of 26, be 11.2% abundant, and have 14 neutrons. Using the mass and the percent abundance, I could calculate the overall average atomic weight. 24 times 0.787 would give me 18.9. 25 times 0.101 would give me 2.53. 26 times 11.2 would give me 2.91. Of course, I'm doing the percents in decimal form. Added together, we would get an overall atomic mass of 24.3 AMUs, or 24.3 grams per mole. If we look at electron energy levels, there are electrons that are close to the nucleus. Those are the ones with lower energy. The energy levels are given a symbol letter N and numbered 1, 2, 3, 4, 5, continuing. Electrons farther from the nucleus, farther out from the nucleus, have greater and greater energy. So electron in an n equal 2 level has higher energy than n equals 1. Electron in n equals 3 has even higher, and 4 has even higher, and 5 has even higher. The energy levels are electrons that are grouped because of their similar energies. The maximum number of electrons that can go in a single energy level is calculated by the formula 2n squared. So the first energy level can hold 2 times 1 squared, or 2 electrons. The second energy level holds 2 times 2 squared, 8 electrons. Level 3 can hold 2 times 3 squared. 3 squared is 9 times 2, 18 electrons fit in the third energy level, and so on. So if we use a certain kind of notation to talk about the number of electrons, we could say hydrogen has 1 electron in the first level, helium has 2 in the first level, lithium would have 2 in the first level and 1 in the second, beryllium 2 electrons in the first level, 2 electrons in the second level, boron 2, 3, carbon 2, 4, nitrogen 2, 5, oxygen 2, 6, fluorine 2, 7, neon 2, 8. Sodium then would be 2, 8, 1, magnesium 2, 8, 2, and so on all the way up to argon 2, 8, 8. Now this is a simplified version of what we learned in Chem 1, 1s2, 2s2, 2p6. 2 s 2 2 p 6. 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 2 s 2 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 2 2 p 6. We're just saying the number of electrons in each level, not sublevels. Electrons can jump up to higher levels or fall from higher levels down to lower levels. When atoms absorb energy, light, heat, electricity, and an electron in that atom absorbs a certain amount of energy, it can jump to a higher level. When the electron falls back down, energy is going to be given off in the form of light. That's why atoms will glow when energized with heat or electricity. So electrons can move from one level to another by absorbing energy or by emitting energy. Absorbing energy makes the electrons move up in energy levels. Giving off energy lets them move down in energy levels. Often when they give off energy, you can see it as visible light. Different colors would be different energies. For example, red is lower energy, violet is higher energy. So this is seen in such things as neon lights, which are energized by electricity and then give off visible light. If you bite down on a Certs breath mint, sometimes you can see a little spark of light. Also, certain kinds of band-aids might give off light when you rip them off. So these would all be examples of electrons falling down energy levels and giving off light. Electron arrangement is important because electron arrangement is what determines the chemical and physical behavior of the elements. That is why there are periodic trends, because of electron arrangements. The chemical properties of the elements, and in a way the physical properties as well, are very strongly influenced by the outer level electrons. Electrons in the outermost level, called valence electrons. And that is why elements in the same group or family have similar properties, because they have similar number of valence electrons. The group number actually indicates how many valence electrons are going to be in a certain element in that group. So groups 1A and 2A have 1 valence electron and 2 valence electrons. Group 3A has 3